2.2 is on limits involving infinity. Now I want you to consider how end behaviors were taught last year. Consider how end behaviors were taught in secondary math 3. If I have some graph like, I don't know, like this, and we're examining the end behaviors, then the first part of my description is always going to be the same. I'm going to say x approaches infinity and x approaches negative infinity. Do you remember this? Does this ring a bell at all from last year? Yes, no, maybe so. I'm not sure if I hear anybody confident about this. Cool. So when I from secondary math 3, when I evaluated this function with the looking at the end behaviors, I first need to consider what happens when x becomes super large. When x becomes super large, what does y do? Does it? I don't see anything up here. It gets way smaller. It shoots off to negative infinity. So we have something, when x becomes really large, y becomes really small. What about when x becomes super, super small? Yeah, y becomes huge. It explodes to the upside. So we're just going to say here that this goes to infinity. And if we add something, so let's re-examine this using limits. So I could do the same thing with limits by writing the limit as x approaches infinity of our function of f of x equals what? Negative infinity. Yeah, negative infinity. So this, what I wrote here is equivalent to what you learned in secondary math 3 right here. So how would I write this other piece right here? How would I rewrite that using our limit notation?
The limit of x.
Wait. Don't go ahead of me. Okay. X approaches what?
Negative infinity.
Negative infinity.
F of x.
F of x.
Equals infinity.
Yeah. Yep. Correct. So that would be equivalent. Yes, sir, Thomas.
Would it be possible for x to approach negative infinity from the negative side?
Would it be possible to approach it for x to approach negative infinity from the what side?
From the positive side.
From the positive. It wasn't that what we're doing from the positive side over here. We're approaching negative infinity.
Well, it's not quite what I meant, but
Technically, you can switch it up just because of because the graph, the f of x that we are currently using is when x gets bigger, y gets smaller, and as y gets bigger, x gets smaller. So it's in the limits have to show that. So technically, the limits could be different. Like x approaching infinity could be the limit of x approaching infinity of f of x could equal infinity. However, that is not the graph we're given, so we can't.
Yeah. So what if we have an opposite like this? So in this case, the limit as x approaches infinity of our function, oh, let's call this g of x. Let's call this one g of x is going to equal what? Infinity, yeah. And the limit as x approaches negative infinity of our function? Negative infinity, yep. What if I have something like this? This is what kind of function? What kind of function? What member or what function family does this belong to? It's exponential. Yep. And so if I look at the end behaviors again, the limit as x approaches infinity of, we'll call this h of x, equals what?
Infinity.
Infinity. What about the limit as x approaches negative infinity of our function?
Zero.
It approaches zero. Yep. We're just looking at we're looking at those end behaviors the same way we did in secondary math 3. We're just writing it differently. What are my indeterminate forms? Do you remember the indeterminate forms?
0/0, infinity over 0, and infinity over infinity.
And so infinity minus infinity, 0 times infinity.
Uh-oh, somebody did a lot more research. All right, so these are the ones that are important, Thomas, and you are right, there are other indeterminate forms, but this is going to be the most common one that you have to deal with. I'm sorry. Is that better? Or infinity over infinity or infinity over 0. Those are the ones that I want you to remember. And sure, Thomas, there are other ones. I do agree with you, but those other ones are for, you'll need to know those for your Calculus 3 class. Class we don't even teach at Highland. So for this class specifically, these are the indeterminate forms that I want you to think of. Now we call them, why do we call them indeterminate forms? Because we can't determine what the limit is just by by substituting, right? That's why they're indeterminate. So let's look at it. Let's look at an example. I have the limit as x approaches 0 of x plus 4 over x.
Oh, that does not exist,
Why?
because you would have 4 on top and 0 on bottom.
Which is not, it's not indeterminate, right? That's not an indeterminate form. If I substitute, I'm going to get 4 over 0, which is not an indeterminate form, which means what is happening when x equals 0? It means one side, I don't know exactly what it looks like, but one side is shooting off to infinity and the other side is, yeah, that's what you have something like that. There's some asymptote that looks like that. And so, and that always is the case when we have, you know, some type of asymptote that we're able to identify there. This one does not exist. Yep. Does not exist. All right, let's do another one. This one's going to be a little bit more difficult. I want you to consider this one. The limit as x approaches 0 of sine of 5x over sine of 4x. Recall our first flashcard. What was our first flashcard? Okay, wait. So our first flashcard is what?
Limit when x is approaching 0.
Yep.
Sine of x over x is 1.
That equals 1. Yep. Is there some way that I can apply our first flashcard to this mess?
There probably is, otherwise you wouldn't have asked that.
Yes, Bryn. There is a way. I just want to know. Remember all those things I said. So Thomas memorized all of the properties of limits, but I said you don't have to memorize them because they're intuitive. Is there a way I can somehow break all this mess up over here using the different properties?
Possibly make like an equal sign and put like the sign of 4x over on the other side.
Sign of 4x.
Yeah.
So so just take this value and move it over here. Wasn't there a law there was some quotient property?
You could, so you can make it so the limit as x approaches 0 of sine of 5x over the limit as x approaches 0 of sine of 4x. So I don't know if that will help.
Of what's this bottom one?
Sine of 4x.
Isn't that a denominator? Oh, actually, we could just write it that way. Does it allow us just to write it that way? Huh, I forgot.
Limit of a function of two functions.
Yeah, we can. Huh. All right, so I have sine of 4x, okay. But we need to somehow, because these oscillate up and down, and if I plug this in, first of all, is this indeterminate? Is this an indeterminate form?
Yes,
Because what is 5 times 0 is 0. What's sine of 0 degrees?
0.
Right, if I look at our unit circle, and sine is our x or y.
Y.
It's our y value. So our 0 degrees, our terminal side and our initial side are the same. And so our y value there is 0. Yep. So this is going to be 0. We have an indeterminate form of 0 over 0. So that we have to figure out how to do this in another way. Is there somehow I can incorporate this in there? If I multiply this over here by 5, I actually don't want a 5, I want 5x in the denominator, which means I have to multiply by 5x over 5x.
You have to do that to both top and bottom. but-
Right, so I'm going to multiply by 1 in the form of what over here? 4x over 4x. Does all of this give me 1? This will give me 1 over 1, which is just 1. Now what? I still need I need to consider the flashcard. Nobody sees it? What is this in the function or to the function? Do I multiply that in the function or to the function? Yeah, do I?
2.
To the function. Yeah, this just goes in the front here.
Oh, yeah, you can get it into a limit.
It's the think time. Or are you guys stuck? Do you guys need think time or are you stuck? We don't have as much think time as we would like because it's a short class today. So I'm going to move this 5x times sine of 5x over 5x like this. The same thing here, the limit as x approaches 0 of 4x times sine of 4x over 4x. Did I violate any rules of math?
No.
No.
Okay. Where do I go from here?
Did you simplify out the 5 and 4?
Yeah, and don't we have a property where if I have the limit as x approaches something of k times a function, what do we get to do with the k? Yeah, can't we do that with the 5 and the 4? What comes in the front? 5/4. Yeah, that gives me 5/4 times this other mess here. Anything, can I eliminate anything else? Yeah, x divided by x is what?
1.
Do you see that or is it confusing?
Not yet.
You don't see how I can take x divided by x and, okay, when we divide by fractions, here's a tip.
Keep, change, flip.
Do you see if I keep, change, flip, then this goes into the denominator over here and then I have x divided by x?
Wouldn't it just be simpler to turn, well, I don't know how legal this is exactly, but if you just turn sine of 4x over 4x using the method that we found yesterday, just to turn the sine of 4x over 4x into 1 and do the same thing with the sine of 5x over 5x. So it's just 5x times 1 over 4x times 1, unless you can simplify from there.
We're almost there. It's already pretty simplified. So do you agree that if I did the keep change flip, would it help if I did a keep change flip to see this where I have 5/4? If I do a keep change flip, then this is 4 down here and 5 up here. And then we have an X here. And then these X's cancel out. Do you see that or not? What's that?
I do see that, but I think it's just a slightly complicated.
So the X's cancel out. For that reason, if I have X over 5 over X plus 6, and I do a keep change flip, then the X's cancel out. Okay. So that's going to give me then the limit as X approaches 0 of sine of 5X over 5X over the limit as X approaches 0 of sine of 4X over 4X.
You cancel 5 and cancel 4.
Can you cancel these out? One is an angle and the other is a length. So we can't. One's inside and the other one's not. So one's an angle and one is not. But isn't that what we wanted to get anyway? Look at our flashcard. Let's look at it. Let's grab our flashcard and bring it down. Isn't that what I wanted to get?
Yeah.
So what's the numerator? What's this mess?
Equal 1, that's the limit of x approaches 0 is 1. Is divided by as the limit of x approaching 0 over 1.
Is 1. Yeah.
So it's just 1 over 1.
So yeah, this is 1 over 1. Do you guys see that? Do you see that I have 1 over 1 here? So what's the answer?
5 over 4.
5 over 4. 5 over 4.
5 over 4.
Okay, let's go back and do this again. Let's completely start over on this. I'm gonna erase all of this mess. Yes, sir.
Honestly, I'm confused about how you got the keep change with the X. How did you take it out of the limit? Oh. wait, no, it's comes 0.
Okay, if you're multiplying, right? And so I'm not taking it out of the limit, I'm doing it inside the limit.
Remember what we did yesterday, or no, it was Tuesday, when it's on the last page, where we got limit of x approaches 0 of sine of 2x over x, and we got the 2. It was the one where you're like, that can't happen.
Yes,
That was
Yeah, it's the same methodology,
yeah, it's the same.
because you're just keeping it's basically because the sine of 4, it's basically you're doing that twice, like pulling out a 5x and a 4x, putting them over into basically 5x over 4x, and then that's what I did at least, because
How did you take the X out? It's not a constant, is it?
It's not, I'm not taking it out of the limit, I'm doing something in the limit. Okay, let's go ahead, let's look at the problem. I think it was at the top, was it? Right here. This one right here, is that, Bentley's talking about this one.
Yeah.
We're doing the same thing, but twice.
you essentially just do what you did with the 2 with the 5x or 4x. And then you do
Okay. So let's do this one again. Keep me honest. What is my first step?
get the end with you
What-
determine.
What if we do that last? Because people are confused about a limit here and a limit here and how are you getting rid of the x's? So let's do that last.
Times the top by 5
I'm gonna-
x over 5x.
Yeah, I'm gonna multiply this one here by 5x over 5x. That's just 1. And I'm gonna multiply down here by
4x over 4.
4x over 4x. That's just 1 over 1, which is just 1. So that's not violating any rules of math. Okay, now what? What do I do with this 5x in the numerator?
Times it to the function.
Yeah, I multiply it to the function. So that gives me the limit as x approaches 0 of 5x times sine of 5x. I have the 5x in the denominator over the sine of 4x, I'm sorry, 4x goes here, over 4x, right?
I guess now, yeah.
If I do keep change flip, do you see how the x's go away?
Yeah, I do.
Okay.
Thank you.
All right, so these x's are gonna go away. We also have a rule that if I set that if I have a constant in a limit, I can do what?
You can take it out.
I can take it out. So that gives me 5 over 4 times the limit as x approaches 0 of sine of 5x over 5x over sine of 4x over 4x. Now we have another law that says that if I have a function over a function, I have the limit of a function over a function, then Thomas, what can I do?
You can separate them.
You can separate them. We can separate, so I still have this 5/4 times the limit as x approaches 0 of our sine of 5x over 5x over the limit as x approaches 0 of sine, I'm getting messy, sine of 4x over 4x. What does this mess here become?
Yeah.
1, because of our flashcard.
Yeah.
Because of our flashcard, it becomes 1. We have all of this is 1 over 1. 1 times 5/4 gives us 5/4. The answer is 5/4. Are we good with that, or is it still confusing? You want me to go further back? Is that too small if I go this far back? Or is it better if I zoom in? Nathan, how do you feel? Do you want me to zoom in? See it? Okay. Should we graph it and see if we're right?
Yeah, sure.
So, all right, so let's graph this. So I'm gonna go to, do I not have a decimal open? So www dot, not YouTube, my word, www.desmos. And I'm going to type in our function. Our function was y equals numerator and denominator. In the numerator, I have sine of, in parentheses, 5x. In the denominator, we have sine of 4x. Crazy. Oh, that hurts my eyes looking at that. Crazy. So what are we approaching? X equals what? Well, we're that. Oh, 0, yeah. So I'm gonna zoom, I'm gonna, so here we have, I'm approaching 0, x equals 0. And oh, we have a hole in our graph right there. But nevertheless, when x approaches 0, y approaches
5/4.
5/4. 5/4, which is, what is that, 1 1/4? Or 5/4. Is that 1.25? 1.25. You see, we're getting closer to 0.25. Do you see that or not? Okay, yep. Oh, that's really close. It's it just rounded to 1.25. But we're not at 0. Let's move over to 0. Can I get 0? I don't know if I can even get 0 now. No, it doesn't want to acknowledge that hole. There we go. There's the hole. Okay.
I was wondering,
Yes.
so like when you take the 5/4 out of the limit thingy,
Uh-huh.
are you also taking the x over x out and then just canceling it? That we just taken the five?
We're doing the x over x in the limit. Okay. So there's not a rule. If I'm trying to find the limit as x approaches something, I'm not going to take the x out. Because that's part of the original expression. The constants can be taken out. But
Then why wasn't there an x in the next part? Like instead of x sine 5x, there was no x. When you took out the 5/4.
say that again. What?
So like when you take out the 5/4, why isn't there an x before sine 5x?
There is. Let's leave it. In fact, let's make sure we understand that. So I'm taking out, in fact, let's leave it in. So we know that, isn't this the same thing then as the limit as x approaches 0 of 5x over 4x times sine of 5x over 5x times sine of 4x over 4x? Is that allowed? Is that the same thing? Because this is the same thing. Let's rewrite it this way. If this isn't convincing, let's do it another way. What if I rewrite this? Let's do this in multiple steps. What if I rewrite this as here 5x over 1, and this is 4x over 1. Is that, do you feel comfortable with that? Isn't that what we do when we have, if I have something like 5, let's do this. Let's do 5 times 1/2. Or let's do something else. Let's do, what if I have 50, let's do this. Let's do this. I have 15 over 5. I can rewrite this as 5 times 3 over 5, right? Could I also write this as 5 over 1 times 3 over 5? Is that okay? Isn't that sort of what I'm doing here? If you look at the original up here, I have 5x times sine of x. This is times, just like this is times.
Yeah.
And so I'm pulling that out in the front, which means it's over 1. Okay, are we good with that?
Yeah.
For the same reason that this works? Okay, now I'm going to just look at this piece. If all, could I also write this then? Because all of this is times, I could write the limit as x approaches 0 of 5x over 1 over 4x over 1 times sine of 5x over 5x over sine of 4x over 4x. Is that okay? Yeah. So let's look, this is all inside of the limit. What can I do with this mess here? Can't we just do keep, change, flip with this piece here?
Yes.
Okay, to get what?
5x over 4x.
Or just 5/4. Yep. So we just get 5/4, and that 5/4 comes in the front, goes out in the front. So one of my arguments is it's Kana, right? One of the really cool things about a lot of people say, it's very common in a math class for students to say, when am I ever going to use this? But the cool thing about higher math is you get repetition, a lot of repetition on the basic math. And so some of this stuff is, this idea of, dividing and multiplying in fractions, that's sort of like a, I don't want to be offensive, but it's sort of like a 4th grade idea. But I understand that was so long ago that you haven't gotten enough repetition. So studying higher math gives you a real strong basis of the basic skills. So even if you're not going to use it, I think it exercises your brain. That's a good benefit, and it also gives you a lot of repetition on the basics. All right, so I'm going to go back. Good, we captured all this on video, so you can go back and watch this piece again if it doesn't make sense, to see why that is, how this works the way that it does. So these cancel out, leaving us with just the 5/4 here. And then these other pieces we can divide. If we have the limit of a function over another function, we can separate those to be a limit of one function over the limit of another function. And that became, this part here became 1. And so we're just left with 5/4, which is what we got when we graphed it as well. All right, we're good. Can we move on? Okay, cool. So let's look at another one. What if I have something like this? This is another example. We have the limit as x approaches 0 of 1 minus cosine squared of x over x. Whenever you see a limit of a trigonometric function, I want you to think of our flashcard, our first flashcard. There's somehow, this is a trigonometric function. I'm trying to find a limit of it. Is there some way that I can rewrite this so it looks like our flashcard of the limit as x approaches 0 of sine of x over x equals 1? Is there something I can do with this? Tate.
Isn't the top one like a trigonometric identity?
It is an identity. What identity is this? It's the trigonometric, it's the Pythagorean identity.
Yeah.
So what is the Pythagorean identity? If we have, so we have this, here's our unit, let's do our unit circle. We have our unit circle. And we have this some point here of our x and y values. That means that this is our x and our y, and then for a unit circle, this radius is what?
1.
It's 1. So if we write this using our Pythagorean theorem, that would be x squared plus y squared equals 1 squared, which is just x squared plus y squared equals 1. But for a unit circle, our x value is what? It's cosine of x. Instead of writing it like this, cosine of x squared, we write it this way, where we have cosine squared x. It's the same thing. You guys know that? Okay. And then plus our y value for the unit circle is what?
Fine.
It's our sine. So we have this is our answer, or our theta or whatever, right? This is our theta. This is our theta if you prefer. So if I manipulate this somehow, is there a way I can rewrite this? Especially knowing I need to incorporate sine. Sine squared of x, yeah. So if I subtract cosine squared of x from both sides, if I subtract, no, that's right. If I subtract cosine squared of x from both sides, I get sine squared of x equals 1 minus cosine squared of x. So this is what I put in the numerator. So that gives us the limit as x approaches 0 of sine squared x over x. Is that what we needed?
No, sine.
Okay, we're one step away. When we square anything, the definition of an exponent, when we square something, it means what? We have 2 of them. So I have the limit as x approaches 0 of sine of x over x times sine of x. Does that look right to you? Okay, now what?
You multiply by 1, it's x over x.
So we're going to multiply by 1 in the form of what?
X over x.
X over x. So that's going to give me the limit as x approaches 0 of sine of x over x times sine of x over x. What do I do with this extra x here?
Leave it for now.
Let's just move it to the front.
Yeah.
Let's just move it to the front here. There we go. So what we have another law that says one of our properties, if we have a function times a function times a function,
We can separate them all.
yeah, we can separate all of them. So that gives us the limit as x approaches 0 of x times the limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of sine of x over x. Does that look right to you? Keep me honest.
Yeah.
Okay. Now what?
It's equal to 0.
Yep.
Yeah.
What is this piece here?
1.
1.
That's 1. What's this piece here?
1.
That's 1. What's this piece here?
0.
How did you get 0?
Because you find it.
Yeah, there's no violations of math to just plug it in right here. So we get 0.
Continuous.
And so it's 0, yeah. The answer is just 0.
And 0 is 0.
Yep. Yes, question.
Please go up.
Yes. How about if I zoom out? Is that better?
How are you able to make the cosine into a sine?
So it's one of our identities, and this is the identity. We need to wrap our heads around this Pythagorean, called the Pythagorean identity. We have a unit circle. A unit circle with a radius of 1, right? So we have, this is our unit circle with a radius of 1. And so cosine, I changed it to a theta. Oh, I changed it to a theta because I don't want you to get confused on underneath here. I want to change that to theta as well. I want to change those to thetas. Okay. So let's do this again. So we have a unit circle with some point here of X and Y. And if it's our unit circle, that means that for X and Y, there's a certain amount of distance here, which is our X, and a certain distance here, which is our Y. And then we have some theta here. Our theta from our initial side to our terminal side, that's the rotation of theta. Now, let's consider what, by definition, what is cosine of theta? The cosine of theta, by definition, is adjacent over hypotenuse. The hypotenuse is 1. So that gives us what? X over 1, which is? X. If I consider sine of theta, by definition, we get? Y over 1, which is Y. Correct? Do you agree with that? Okay. Now let's consider the Pythagorean theorem. If I use the Pythagorean theorem here, then what do I get? X plus Y squared equals 1 squared, or just 1, right? But we saw that X is cosine. So what if I substitute those in? And that gives me cosine squared of theta plus sine squared of theta equals 1. Most of us just have this memorized. We don't have to go and recreate it each time. We just have it memorized.
I see the way you wrote down punching that.
Back here?
Yes.
Okay, so I just did this.
Not that, just like the.
You want me to zoom out?
solve the limit.
Okay. So what I did is, since I have this Pythagorean identity, and so what I did is I subtracted cosine squared theta from both sides, giving me what we have in the numerator here. So I replaced that with sine squared theta, or in this case, sine squared of X. It's one of our identities. That is something you might, if you don't know about that identity, you might want to make that one of your flashcards. Was this a secondary math 3 idea?
Yeah.
Did you guys learn that last year in secondary math 3? Yeah, okay. So, and all of us have holes in our math, so there's no criticism at all from here. If there's something that looks confusing, please tell me. I want to make sure that we understand it. So we're going to move on then. What if we have something like, I want to look at 3 different possibilities. This is also right now I'm going to talk about another secondary math 3 idea. This is also another secondary math 3 idea. Now, if we have so we're talking about rational functions, rational functions. What's a rational function defined as an equation? It's defined as a polynomial divided by a polynomial. That's the definition of a rational function, whenever we have a polynomial divided by a polynomial. So we have some polynomial. We have a times x to the power of n plus ... The leading term is the only thing that really matters when we're talking about end behaviors. That's what we're talking about today, is end behaviors, right? That's when x becomes, when we're talking about limits as involving infinity, even though I guess our first examples did not involve infinity. These were just more of, some examples from last time. All right, so I have a polynomial divided by some other polynomial of b times x to the power of m plus ... when we're talking about end behaviors, the other stuff doesn't matter. So this is a secondary math 3 idea. If n, there are 3 different possibilities. Either n is less than m, or n equals m, or n is greater than m. What are, when we have a value, when we have functions like that, where the degree in the numerator is smaller than the denominator, then we always have a certain type of horizontal asymptote. Do you remember what it is? Consider y equals 1 over x. We're looking at end behaviors. If we're looking at end behaviors, we're talking about when x becomes super large or super small. What do we converge on when x is massively large? 0. So this is always going to be the case. If our numerator has a smaller degree than the denominator, the horizontal asymptote will always be y equals 0. We converge on y equals 0. All right, let's consider what if they're the same. What if I have like x over x? Remember, the other stuff doesn't matter, right? It doesn't matter when x becomes massively large, right? If I have x squared plus 5x minus 6 over x squared minus 3x plus 2, when x is massively large, these values here become irrelevant, or they become very insignificant when x is massively large. What value do we converge on when x is massively large?
Would be y equals x.
Be 1.
Yeah, in this case, it's 1. In this case, well, what if I have something else like here? What if I have something like this here?
That's what.
Yeah, it's going to be 5. Yep. We converge on 5. So in this case, our horizontal asymptote is always going to be y equals a over b. You guys remember this from last year? A little bit, Bryn?
Yeah,
Okay. Well, I know who your teacher was last year, so if they didn't teach it very well, I'm going to have a word with them. All right. So what about the next one? What about if the degree in the numerator is greater than the degree in the denominator? What if we have something like this? What if we have something like 3 up here? When x is massively large, what do we converge on? Infinity. Yeah, we just shoot off to infinity. This is going to overpower the denominator so much that we just shoot off to infinity. So there is no horizontal asymptote. So none. There's none. No horizontal asymptote. All right, consider this then. What if I have the limit as x approaches infinity of 3x plus 1 over 4x squared plus 5? What is the answer?
0.
Why is it 0? Because of our horizontal asymptote. We're converging. We have n is less than m, so we converge on y equals 0. So the answer is 0. Are we good with that? Okay, moving on. What if I have, let's move in, I have the limit as x approaches infinity of 3x squared plus 5x minus 6 over 4x squared minus 6x plus 2.
3/4.
Why?
Because n equals m.
What happened to all these?
Irrelevant.
They don't matter. These numbers are going to be so much more powerful, so much larger. When x becomes large, these other values are going to be so much larger that it doesn't matter. Imagine Bill Gates. Isn't he a billionaire?
Probably.
You go offer him $5. Does he care?
No.
No, it's irrelevant to him. It doesn't change anything for him if you go give him $5. It's these other numbers that matter. So that we end up getting, what's the answer again? What's the answer? 3/4. One more time, why is it? Consider our rules, consider our rules. Why, let me back out. Why is it 3/4? Because n equals m. Yep, because n equals m, or degree in the numerator is the same as the denominator. Okay, let's look at another one. I do have some other flashcards. Here's our second and third flashcard. Our second flashcard. This is second flashcard. Is anybody taking my advice about flashcards?
Yes.
Awesome, cool. Yeah, if your teacher says to do it, maybe you do it. Right, so we have the limit as x approaches infinity of sine of x over x. And then we have the limit as x approaches infinity of cosine of x over x. These are the next, this is the second and third flashcard. Now, we have to remember these because what happens with all periodic functions is oscillation. We're just going to oscillate up and down, up and down, up and down, up and down. So I want to know what's happening when we get to extremes. So let's go to Desmos and just take a look at what if I have y equals sine of x over x. Any ideas by looking at this, when x becomes massively large, what we converge on?
0.
Yeah, we're converging on 0. We are converging on 0. All right, let's look at the next one. What if I have cosine? What if I have cosine of x? Cosine of x looks like this. Any guesses what we converge on with cosine of x over x? What's that? Louder?
0.
0. Nice. We're converging on 0 as well. So we're going to say 0 for this one as well. These are your flashcard number 2 and flashcard number 3. We need to make sure we're learning these as we go. You do not get a formula book for the AP test. You have to have everything memorized cold. So those are the next 2 flashcards. All right, so using these flashcards, how am I going to figure out? I want to find the limit as x approaches infinity of 5x plus sine of x over x.
That's like an S.
Better?
Yes.
How about if I just start over? How about if I start over? Are you good with that?
Yeah, that's nice.
Awesome. You get it?
Yeah.
How?
Okay, well, the first thing I did is I used the sum rule and just separated the 5. Oh, that's it. No, that's not it. That's not it. It's
Oh, okay. First thing you did is what?
I separated the terms.
We have a rule that if I have a plus b over c, I can rewrite this as what?
AC plus BC.
AC plus BC, correct?
Okay.
Is everybody correct, comfortable with this rule?
Yes.
Okay, so that means I can rewrite this how?
5x over x.
Okay, so I have the limit as x approaches infinity of 5x over x
Plus sine x.
plus sine of x over x, okay?
And now you do the sum rule. Yeah.
Before the sum rule, can't we simplify this a little more?
We can.
Yeah, we just get 5. So now we're going to do the sum rule where we just have 5. So I have the limit as x approaches infinity of 5 plus the limit as x approaches infinity of sine of x over x. Okay.
Yeah, the first thing's 5.
Okay.
0. 5 plus 0.
So when x becomes super, super large, y converges on what?
5.
In fact, y is always 5, right? Y is always 5. So I have 5. So I have 5 plus what?
0.
Yeah, 5 plus 0. This is 0. 5 plus 0. So the answer is
Five.
Yeah, this is 5 plus 0 or just 5. Brandon, are you going to criticize my 5?
No, it was just that one where it's like, for some reason, whenever you have 5x, it gets hard to read for some weird reason.
I actually do want you to correct me. If it's confusing, then just let me
Yeah,
know.
well, it's fine. It's just like, when it's 5x, I think that it must be probably why dyslexia wants me to be sin x,
Okay.
but it's not. And so it's like, if there's, especially if there's a sin x really close by.
Right. Let's look at the end behavioral model. I want to look at what's called, how much time do I have? 5 minutes? Gosh, I hate crunch time like this. Okay, end behavioral model. End behavioral, well, I think it's just called the end behavior model. End behavior model. If I have something like f of x equals 3x squared minus 2x plus 1. If I'm talking about an end behavioral model, then I'm not saying that it's equal. We're just saying that it has the same, that the pattern is going to be the same with this equation as it would for this equation. Okay. We're saying that the end behavior, the characteristics of this end behavior is the same as this. Do you understand how I got that?
Yes,
Why? What happened to these?
they are insignificant.
They're not, yeah, they're not important when x is really, really large. Okay, let's look at another one. What if I have g of x equals x minus 2 over 2x squared plus 3x minus 5? What is my end behavior model for this one?
0.
I have x over 2x squared. Can I simplify that even more?
Pretty much 1.
1 over,
2x.
that is my end behavioral model.
So we just look at the first term. and then simplify?
Yeah, because the end behavior, you're talking about when x is massively large. Okay, when x is really, really large, the other stuff doesn't matter. Okay, let's look at another one. What if I have this one? H of x. I have 4x cubed minus 2x plus 1 over x minus 2. What is the end behavior model? 4x. Is that Tate? Is that Tate?
Yes.
Good job, Tate. How did you get that? Look at the first two terms, okay? And then simplify. Are we good with that?
Yes.
Okay, let's do another one. J of x. Looking at the end behavior model. Yes.
Negative x squared.
Negative x squared. Yep. We're looking at the leading terms, right? The leading terms in this case are this one and this one. That one's not written in descending order of exponents. So that's going to give us this as our end behavior model. Do you have time for one more? Una más? Okay, so now this is the last one. K of x equals 10x squared plus 5x plus 4 over 2x squared minus 6x plus 3.
Just 5.
Yeah, just 5. Our end behavioral model is just y equals 5. That's what happens. I'm not saying it's equal, right? There's no confusion that I'm not saying that they're equal. I'm saying that the end behaviors will be equivalent. That's what I'm saying.